Hey, what's up, guys? Back at you today. Nice work on the test today. I saw a lot of good work out there. I know those problems can be tough, um, but on the bright side, I think you'll find this standard to be very nice and very easy to use. The local linearization type points that you get on the test often tend to be some of the easy, in my opinion, some of the easiest points to earn on the test. So it's ones that we really need to get right. This sounds kind of like a confusing topic by the name, but it's actually pretty simple. So this is local linearization. So kind of the concept behind local linearization is that in calculus we from time to time deal with linear functions, but almost everything we deal with, every function is a curve of some kind. Okay, so I'm just going to go back to my calculator app here real quick. I want you to take a look at it with me. When I take a look at the picture of this graph here, clearly this graph does not look like a line, right? This is clearly curved. Okay, and what I want you to do, kind of follow my cursor here. I want you to focus on this stretch of the graph right here. Clearly this graph is curved, right? We would say it looks like it's concave down, right? If this is our graph of f, okay? So clearly we're dealing with a curved graph here. But the word local means, right? If you're supposed to shop local, that means you buy your products and food and clothes from people right in your own neighborhood. So thinking about that concept, local linearization means that even curved functions, when we look at just a little area, they start to look like lines. So I'm going to use what's called the zoom box feature to kind of zoom in on this area. Again, this part of the graph, right, this graph looks very curvy. But if I zoom in on an area, we're going to see what it starts to look more and more like. So if you are curious how to do the zoom box, if you hit zoom, it's option number 1. I don't use it very often, but it's kind of a cool function. When you hit zoom box, you can move your cursor around, and what you can do is create a box that you want to be zoomed in on. So I'm going to zoom in on that function we were kind of looking at. So when I'm ready to make the box, I hit enter. And now I'm going to arrow up. And then arrow over. And what I'm going to do is I'm just going to make my whole screen what's in the box that I created here. So my new picture will just be, this will be like the full screen. So I'm zooming in just on this piece right here when I hit enter. When I do that, I can see, okay, I can definitely tell that this is still curved, but it's starting to look much more like a line than it did in the last picture. Okay, I'm going to do zoom box one more time and zoom in even closer on this curve. I'll start it right here. Arrow up a little bit. Sorry, your calculator will be faster at doing this than this calculator app will. I'll hit enter again. As we see now, the more and more we zoom in, right, my window now is very, very tiny. This graph right here looks very much like a line, even though it's the exact same graph that I've been looking at the whole time, right? The function it looks like is sine of x squared. So this graph right here, although not a line, when I have like a small enough neighborhood I'm looking at, it acts like a line. So what we're able to do is we're able to estimate points in a local area with a pretty good amount of accuracy based on the tangent line to the function. Okay, so let me show you what this looks like. I'm just going to do a couple examples here. This video shouldn't be too long. let's say we know about a function. We know about a function f of x. Here's what we know about f of x. We know that f of 3 equals 5. And we also know the derivative at 3 is, I don't know, let's say 2. Choose easy numbers here. Okay. Well, some of the questions that we might have to answer are, I want to estimate f of 2.8 using the tangent line to f at x equals 3. Okay. So right now there's no way I could ever figure out what f of 2.8 is, because I don't know f of x, right? If I had f of x, I would just plug in 2.8 and see what it gave me. Now, just thinking about this, f of 2.8, since we know f of 3 is 5, f of 2.8 should be some number that's pretty close to 5, right? But is it going to be a little bit above 5? Is it going to be a little bit below 5? Right? Those are the things that we kind of have to ask ourselves, right? And that we'll be able to answer using local linearization, right? Or maybe you know it's going to be less than 5, but is it going to be 4.9 or 4.8 or 4.7 or 4.6 or somewhere in between, right? So let's think about this. We want to estimate f of 2.8 using the tangent line to f at x equals 3. So obviously this is telling us we need an equation for a tangent line to f at x equals 3. So one of the things we want to think about is, how do we write an equation of a tangent line? Well, dust off your old calculus brain here and know that for an equation of a tangent line, we always need a point and a slope. Well, the nice thing is, those are given to us, right? We know x is 3. Well, when x equals 3, what does y equal? Well, it's right here, 5. How about the slope? Well, that would be f prime of 3. Oh, they also gave that to us. Oh, that was easy. Okay, so now I just want to write the equation of the line. Oops. Easy, right? So what we're saying is, for numbers really close to 3, and 2.8 is a number really close to 3, this tangent line is going to give us a pretty good idea of what's going on. Okay? So we can use this. We can use tangent lines to estimate points really close to where we know that tangent line equation at. Right? So if we think about this on a graph, right? All I know about f is it has the point 3, 5. Right here. And I know right at that instant, the slope is a slope of 2. But I don't know exactly how it goes, but all I know is the tangent line slope right here should be 2. Well, so this line right here is f, right? Let me redraw that picture real quick. So maybe f looks something like this. Okay. What I know is the slope of the tangent line, or I know the equation, sorry, of the tangent line right here. So this is our tan line equation. So since we don't know what's happening with f, right? We can never find f of 2.8, right? We're gonna evaluate our tangent line equation at 2.8, and that's going to be a pretty good guess of what f of 2.8 is. It's going to be the best guess we can do here. Okay. So what I need to do now is, so again, This right here is my tangent line. What I want to do is take the point that I'm estimating, right? We're supposed to estimate f of 2.8. Well, I'm going to take that 2.8 and I'm going to plug it in for x right here and figure out what y is, and that'll be our best guess of f of 2.8, right? So this is a pretty easy process from here on out. So here's what I get. I get y minus 5 equals 2 times 2.8 minus 3. Now I have to do 2.8 minus 3, and that comes out to be negative 0.2. Now I have to do 2 times negative 0.2. 2 times negative 0.2 is negative 0.4. And now I just have to add 5. Negative 0.4 plus 5 is the same as 5 minus 0.4. 5 minus 0.4 is 4.6. So that is the exact point on my tangent line. Right? We don't want to leave our answer like that, though, because we're supposed to estimate f of 2.8. Well, our best guess for 2.8 is that f of 2.8 is approximately equal to 4.6. Okay. So again, it makes sense that my answer is an answer close to 5, but notice it ended up being a little bit less than 5, 4/10 less. Okay. So that's the kind of stuff we'll be looking at on Monday, right? So we'll look at examples of that type of stuff in class on Monday. That's it for tonight, a short one. Local linearization is really fun. Hopefully you enjoy it. It's really easy, and there are points that we need to make sure we hit on the AP exam. See you guys Monday. 2 chains, bye.